Click the bell icon to get latest videos from Ekeeda.
Hello friends, in this particular video session we will learn the next step of the integrator part that is called as differentiator. Now exactly opposite to that of integrator, we are looking for differentiator. Mathematically, the difference between two quantities in a very short span of time, that is nothing but your differentiation, and that mathematical term differentiation, we are converting it into your circuit point of view, and that is nothing but your differentiator. Hello friends, in this particular session, we will start with new topic that is differentiator. Differentiator is nearly same as that of ulta of integrator. Integration may we are trying to get the output in the form of integration of that of your input. But here we are taking the output which is in the form of derivative of the input signal. So this derivative concept we are converting it into circuit point of view, that is nothing but the differentiator with operational amplifier. First of all, we will look the mathematical expression of the differentiator if we are expecting that the output should be in the function of input signal, then how it will behave with respect to your input. VO is your output signal. Let us consider that is in the time domain. That should be equal to some constant value multiplied by derivative of input signal with respect to time. So obviously this V in must be the function of time, and this complete expression is called as differentiator. And this concept we are converting it into circuit, which is giving me the differentiation. In the integrator circuit, we placed feedback में capacitor instead of resistance RF. Here we will place capacitor in the input signal, and in the feedback circuit we will place the resistance RF. Just we are swapping the placement of resistance R and capacitor C. Negative, positive, this is ROM, and this is how simple differentiator. Simple differentiator. We will take the look at mathematical expression, mathematical derivation, how we will be getting this kind of expression if we are having this circuit in the form of operational amplifier as an active device and these resistances and capacitor as passive device. We will apply KCL at this particular node. First of all, we should get to know that what is the current flowing through the capacitor. As we all know that current flowing through the capacitor this is the current flowing through the capacitor. Now question arises, what will be the value of VC? If you look at this particular capacitor, we will say that this is nothing but the VC. Then your V in minus VA is your value VC. VC is equal to V in minus VA. But what is the value of VA? We all know that what is the virtual ground concept is saying, as this is nothing but the open circuit. If this is open circuit, then we will not be having any kind of current which is flowing through ROM, and that is why voltage drop across ROM is 0, as no current is flowing through resistance ROM. Voltage here will be 0. If this is 0, then this has to be 0. So with virtual ground concept, with VG concept, we will be having VA is equal to 0 volt. Great. If VA is equal to 0 volt, now I can say that VC is equal to V in. I can put VC ke jagah V in. IC is equal to equation number 1. Now I will apply KCL. Apply KCL at node number A. KCL at node number A. Applying KCL at node number A, here I'll again represent this. This is nothing but resistance RF, and this is a capacitor Here it is again open circuit. V in. Current flowing through the capacitor, let's say IC, because representation of VC is like this, plus and minus, so direction has to be from positive to negative. Incoming node, and this is outgoing away from the node, current IRF, and this is current IC. We can say that IRF is equal to IC. What is the value of IRF? IRF is showing that this is 0 and this is nothing but connected to output voltage VO. IRF is nothing but 0 minus VO divided by resistance RF is equal to, we'll make use of this equation number 1, C into dV in divided by dt. We can get VO is equal to minus C RF multiplied by dV in divided by dt. This is the expression that is nothing but showing that output voltage VO is a function of derivative of input voltage Vin if both are in time domain. Now we'll have to go for the consequences we face at infinite frequency and zero frequency as well. We can convert this complete VO term. Initially we are having, let's say, this is nothing but your expression in the form of time domain. So we can represent this is in the form of RF into C multiplied by D into Vin of t divided by dt. This is in time domain. I want to convert this into frequency domains. So we will make use of Laplace transfer fundamental, where we can convert this d by dt into simple s. S is nothing but j omega, which is nothing but frequency. We will say convert time domain to frequency domain. We will be getting VO of S is equal to minus RF into C, that is all okay. And here we will be getting S. Now if you look this carefully, obviously this is nothing but multiplication with V in. So that we will be getting VO of S divided by V in of S, which is nothing but gain, which is equal to minus RF C into S. Now this is the crucial formula, minus RF S into C. We'll put the value at S is equal to 0. That means frequency is equal to 0, your gain is equal to 0. That is okay. Gain is equal to 0. And if frequency S is higher and higher, what will happen? Your A is equal to infinite. A is equal to infinite. So that is showing the positive slope passing through 0, passing through origin, which is not feasible, which is not practically possible. This is because your input resistance is also one of the factor. There are two major factors come into play with the consequences limitations of simple integrator. One is the characteristics at omega is equal to infinite, gain will become infinity, which is not at all possible practically. And if I am saying that the input resistance, what will be input resistance at omega is equal to infinity and omega is equal to 0? If omega is equal to 0, this will become open circuit. At omega is equal to 0, this will become open circuit, and omega is equal to infinity, this will be a short circuit. I don't want that short circuit. I want to keep that value R as it is. This is because I want that RF divided by R. If R is equal to 0 at omega is equal to infinity, then what will happen? RF divided by this particular impedance, which is 0, then your value of gain will become infinite. So what will happen? I will not get the proper output at omega is equal to higher values. We will make a change in this particular circuit such that here with RF we will place the capacitor, and with capacitor we will place the resistance so that both the consequences get rid of. That is, one is your impedance and another is your gain parameter. Simple circuit which includes resistance R with capacitor and capacitance C with resistance. Let's say this is C1, this is CF, this is RF, VO, Vin. Now just I want to make sure that VO divided by Vin is nothing but minus of this Z divided by this Z. So we will treat this Z as Z2 and this as Z1. So Z2 minus Z1 I have to calculate. I have to form a transfer function by using Z2 minus Z1 with CF RF and C1 R1. So you can easily calculate what's the value of Z2, what's the value of Z1. So take a pause of 2 minutes and try to evaluate what's the value of Z2, what's the value of Z1, and take the ratio of Z2 and Z1. That will be your transfer function altogether. This is the value of Z2 and Z1. We will take the ratio of Z2 and Z1, so that we'll be getting the gain. Gain is equal to VO of S divided by Vin of S, which is nothing but RF upon 1 plus RF CF into S divided by 1 plus RS C1 multiplied by you can get this will go up, which will give you RF into S into C1, and here we will be getting 1 plus R into S into C1 and 1 plus RF into S into CF. Nice. Now here we will be getting 1, 0, which is at origin, which shows that the slope is incremental in nature. If we draw the characteristics of the practical and ideal differentiator, then we will be getting that. The ideal differentiator is something like this. This is the ideal differentiator, which is increasing from 0 to infinity. Simple differentiator. This is simple differentiator. And now we have to learn that with this particular pole zero graph, how we can evaluate the graph of this particular practical integrator and how it is practically possible. Up to certain value of corner frequencies, I will be getting a 0. That is nothing but this particular, let's say, minus 20 dB per decade. If you know Bode plot, then you will get very easily the nature of this graph. Then we are getting one of these pole which compensate with your 0, and then again we will be getting the, at a very high value, you will be getting the decremental nature, which gives you the nature of band pass filter. Somehow it is high pass filter only because this particular value is very high, such that I can neglect that part and I can treat this as a high pass filter. Okay, so that gives you the differentiator which will act as band pass filter or high pass filter that depends on the value of RF and CF, which is nothing but the time constant. So 1 upon RF CF is nothing but the one of the corner frequency. R into C1 is another corner frequency, and RF and C1 is another corner frequency. We can say that this is your RF C1, this is your R into C1, and here we will be getting the RF into CF. So with this, we conclude that even though the frequency increases to infinity, gain will no longer as infinity, which is well below the infinity, which is nothing but the practical value. So far we have discussed the practical implementation of the differentiator using operational amplifier with both conceptually, mathematically, practically, and ideally. I hope you enjoyed this video. If you like this video, then do like, share, and subscribe, and also comment on this particular video. Thank you so much.